The last star has gone dark. There is no light from another galaxy, no warm planet, and no sky that can still be called night. The word night only has meaning when we expect morning to return. In the farthest future, that morning may never come. Before the universe reaches such darkness, what will happen to the stars, the galaxies, the black holes, and the matter from which everything was made? Will the ending be a slow fading into equilibrium, a violent tearing apart of space, or a collapse back toward the conditions from which the cosmos began? We will begin in the present and let the clock move forward. A billion years becomes a trillion. A trillion becomes a number so large that ordinary language begins to fail. The first image is still familiar. The Milky Way shines across the sky, distant galaxies fill every direction, and the faint afterglow of the Big Bang remains throughout space. Our universe is about 13.8 billion years old. That sounds ancient until it is compared with the future. Most of cosmic history may still lie ahead. The age of stars could be only the opening chapter of a story, whose final pages are almost unimaginably distant. The future is not known with certainty. Cosmology can extend tested laws into new eras, but the farther we travel, the more every prediction depends on assumptions. We will separate three things. Some events follow strongly from established stellar physics. Some depend on quantities we are still measuring. Others remain possible solutions, not confirmed destinies. Our first stop is much closer than the death of the universe. It is the future of Earth and the Sun. The Sun is a middle-aged star. It shines by turning hydrogen into helium in its core, slowly changing its internal structure as it ages. Over roughly the next billion years, the Sun will become brighter. Long before it becomes a red giant, that increasing energy may destabilize Earth's climate and oceans. Exactly when Earth becomes uninhabitable depends on feedback between the atmosphere, the oceans, geology, and life. The broad direction is more certain than the precise date. In about 5 billion years, hydrogen in the core will be largely exhausted. The core will contract while the outer layers expand. The Sun will become a red giant, far larger and more luminous than it is today. Mercury and Venus are expected to be engulfed. Earth's fate is less simple. The expanding solar surface may reach our orbit, while mass loss from the Sun pushes the orbit outward. Tidal forces and drag inside the giant atmosphere make the final outcome difficult to calculate. Even if Earth avoids being swallowed, it will no longer resemble a habitable world. The Sun will eventually shed its outer layers into space. For a short cosmic moment, those gases may glow as a planetary nebula. At the center, the former Sun will remain as a white dwarf, an object about the size of Earth, with much of a star's mass compressed inside it. No new fusion will support it. It will cool for an extraordinary length of time, fading toward blackness. The end of our Sun is not the end of stars. Across the universe, new stars will still be born inside cold clouds of gas. But the supply is not infinite. Every generation locks some matter inside stellar remnants, planets, and objects that no longer return enough material to the next nursery. Galaxies also change. The Milky Way and Andromeda are moving toward each other, although newer measurements have made the details of their future encounter less certain than older, simpler diagrams suggested. They may collide directly, pass in a wide encounter, or experience a more complicated sequence influenced by the rest of the local group. If they merge, individual stars will rarely strike one another because the distances between them are enormous. The shapes of the galaxies, however, will be transformed by gravity. Gas may be compressed into new stars, orbits will be rearranged. The familiar spiral structure of the Milky Way will not survive forever. Meanwhile, on the largest scales, space continues to expand. Distant galaxies are not simply flying through a fixed emptiness. The distances defined by the geometry of space are increasing. Observations indicate that this expansion is accelerating. We use the name dark energy for whatever is responsible, while admitting that its physical nature remains unknown. If accelerated expansion continues, galaxies beyond our gravitationally bound neighborhood will recede until their light can no longer reach us. One by one, they will cross a cosmic event horizon. They will not crash into a wall. Their signals will simply become more stretched, fainter, and eventually inaccessible. A civilization living in the far future, inside the merged remains of the local group, might look outward and see almost no evidence of other galaxies. The cosmic microwave background will be redshifted to wavelengths that are extremely difficult to detect. The universe may appear far smaller and more isolated than it appears to us. That future civilization could develop excellent physics and still have less observational evidence for the Big Bang than we possess today. Cosmic knowledge is not only a question of intelligence. It also depends on living at a time when the evidence is visible. Now the clock accelerates again. Large blue stars burn brightly and die quickly. Sun-like stars live for billions of years. Red dwarfs, the smallest true stars, use their fuel with remarkable patience. Because their interiors can circulate material efficiently, they may burn hydrogen for trillions of years. The universe will spend far longer under the faint red light of these stars than under the bright constellations we know. A planet near a red dwarf might experience a long, stable source of energy, although flares, tidal locking, and atmospheric loss could shape whether such a world remains habitable. The final ordinary star may not resemble the Sun. It may be a tiny red ember, using the last fraction of hydrogen with extraordinary efficiency. Around it, the sky will be almost empty. Most galaxies will already lie beyond reach. The remaining local stars will be old, dim, and widely separated. Eventually, even the longest-lived red dwarf will exhaust its fuel. Some models suggest that it may pass through stages, unlike the red giant future of the Sun, becoming hotter and bluer, before settling into a white dwarf. Then the stellar era ends. The universe enters what is sometimes called the degenerate era, dominated not by shining stars but by their remnants. To appreciate how different that era will be, imagine removing every familiar point of light from the sky. White dwarfs begin hot, but without fusion, they can only release the heat stored inside them. Their glow shifts toward red and infrared, then becomes too faint for any ordinary eye. A fully cooled white dwarf is sometimes called a black dwarf. The universe is not old enough for even one to exist today. Forming one requires times far greater than the present cosmic age. Neutron stars cool as well. They preserve extraordinary density, with more mass than the Sun compressed into a sphere roughly the size of a city. Their magnetic fields decay. Pulses that once crossed space like lighthouse beams eventually fade. Brown dwarfs never became massive enough to sustain ordinary hydrogen fusion. In the dark future, they remain as cold objects, somewhere between giant planets and small stars. Planets may continue orbiting these remnants, but without a star, their surfaces approach the temperature of the surrounding universe. Some energy can survive below the surface. Radioactive elements decay. Tidal forces flex interiors. Chemical reactions proceed in protected environments. Yet every reservoir is finite. Without a new gradient, each source of usable energy becomes weaker. Orbits also evolve over immense periods. A passing remnant can disturb a planetary system that appeared stable for 1 trillion years. A planet may be thrown into darkness between galaxies. Another may fall into a white dwarf, briefly creating a disk of hot debris. The future is therefore not perfectly still. It is active in isolated flashes, but the silence between those flashes grows longer. White dwarfs, Neutron stars, brown dwarfs, cold planets, and black holes continue to orbit through darkened galaxies. New light may still appear occasionally. Two brown dwarfs might collide and create a star with enough mass to ignite hydrogen. White dwarfs might merge. Compact objects might collide. But these events become rare flashes separated by longer and longer intervals. Gravity continues its slow sorting. Encounters can eject objects from galaxies, leaving cold worlds to travel through intergalactic darkness. Other objects lose orbital energy and fall towards central black holes. At this point, one of the largest uncertainties in particle physics becomes important. Are protons perfectly stable? No proton decay has ever been observed. Experiments have shown that if it occurs through many proposed channels, the lifetime must be enormously long. If protons do decay, ordinary matter eventually dissolves into lighter particles and radiation. Planets, white dwarfs, and neutron stars would not remain forever. If protons are stable, matter could survive in altered forms for far longer. Other quantum processes may still transform compact objects, but the timeline changes dramatically. This is why a distant future diagram is not a calendar carved into stone. It is a map whose roads depend on discoveries we have not yet made. As eras pass, black holes become increasingly important. A black hole is not an empty hole in the ordinary sense. It is a region where space-time is curved so strongly that beyond the event horizon, no signal can return to the outside universe. Stellar mass black holes remain from collapsed stars. Supermassive black holes occupy the centers of galaxies. Some contain millions or billions of times the mass of the Sun. They can grow through mergers and by consuming surrounding matter. In the dark future, however, the available material becomes sparse. Black holes appear perfectly black in classical general relativity. Quantum theory changes the picture. In the 1970s, Stephen Hawking showed that quantum fields near a horizon allow a black hole to emit thermal radiation. The black hole loses energy and therefore mass. Smaller black holes are hotter and evaporate faster. Larger ones are colder and survive much longer. For any black hole we know, Hawking radiation is far too faint to observe against the present cosmic environment. But the universe cools as it expands. Eventually, the surroundings become colder than the black hole, and evaporation dominates. A black hole with the mass of a star may require around 10 to the power of 67 years to disappear, depending on its mass and the particles available. The largest supermassive black holes may survive for times closer to 10 to the power of 100 years. These numbers are not merely longer than human history. They are longer than the present age of the universe repeated, more times than language can comfortably express. During most of that era, very little happens near any one location. Then, toward the end of its life, a shrinking black hole becomes hotter. Its radiation intensifies, and the final stages proceed rapidly. The exact final moment requires a complete theory of quantum gravity, which we do not yet have. Hawking's calculation tells us the broad direction, not every detail of the last instant. Imagine the last black hole completing this process. For an immense time it has been one of the final structures capable of storing concentrated energy. Then it is gone, leaving only dilute particles and radiation. What remains is the leading ending described by the current standard cosmological picture: heat death. The phrase sounds like an explosion or a burning universe, but it means almost the opposite. Heat death is a state approaching maximum entropy, where energy still exists but no longer has useful differences that can drive complex processes. Entropy is often described as disorder, but that word can be misleading. In thermodynamics, it is more useful to think about how many microscopic arrangements can produce the same large-scale state. Concentrated energy occupies a special condition. A hot star beside cold space provides an obvious direction for energy to flow. When energy spreads through every available degree of freedom, there are vastly more ways for the system to look ordinary, and far fewer ways to recover the original concentration. This is why a broken cup does not spontaneously leap from the floor and rebuild itself, even though the microscopic equations do not simply forbid every reverse motion. The reverse arrangement is so extraordinarily unlikely that it is never observed at human scales. On cosmic scales, gravity adds complexity. Gravity can cause matter to clump, forming stars and black holes, while the total entropy still increases. Black holes carry enormous entropy. Their horizons become major entries in the universe's thermodynamic accounting. When black holes finally evaporate, their concentrated mass becomes widely distributed radiation. The process continues the overall movement towards states with fewer accessible gradients. Heat death does not mean every point has exactly the same temperature at one precise moment. Horizon, expansion, quantum fluctuations, and isolated particles complicate the picture. It means that the universe trends toward a condition where organized work becomes overwhelmingly difficult, because useful differences have been exhausted. There are speculative discussions about rare fluctuations in an almost empty future, or about whether de Sitter space possesses a finite temperature and entropy. These questions lead into difficult territory, where quantum theory, gravity, and cosmology meet. They do not provide a practical rescue for stars, planets, or civilizations. Even if an extremely rare fluctuation occurs after an absurd interval, it does not reverse the broad thermodynamic history of the observable region. A heat engine needs a hot place and a cold place. A star shines because energy flows from an extremely hot interior into a colder environment. Life also depends on gradients. Earth receives concentrated sunlight and radiates lower temperature energy into space. If the universe approaches equilibrium, those differences become harder to find. There may be particles, photons, and quantum fields, yet almost no accessible free energy for stars, machines, or metabolism. The expansion of space continues to dilute matter and radiation. Distances grow, interactions become rare. This ending is not a single dramatic night witnessed by the entire cosmos. Different regions lose access to one another. Structures fade at different times. There is no universal audience gathered for one final sunset. Heat death is less like a candle being blown out, and more like a room in which every temperature has slowly become the same. Why do scientists treat it as the main possibility today? Measurements indicate that the universe is close to spatially flat on large scales, and that its expansion is accelerating. If dark energy behaves like a cosmological constant, with a density that does not dilute as space grows, accelerated expansion continues indefinitely. That leads naturally toward isolation, cooling, black hole evaporation, and an increasingly uniform state. But dark energy remains one of the deepest unknowns in physics. Its behavior determines whether other endings remain possible. One alternative is the Big Rip. In this scenario, dark energy has a property sometimes described by an equation of state parameter less than -1. Its effective density increases as the universe expands. Acceleration does not merely continue, it becomes stronger without limit. At first, distant galaxy clusters lose contact. Later, galaxies themselves can no longer remain gravitationally bound. As the effect strengthens, solar systems are pulled apart. Then planets, molecules, atoms, and perhaps spacetime itself are disrupted. Unlike heat death, the Big Rip can occur after a finite amount of cosmic time. The timetable depends entirely on the properties of dark energy. Current observations do not establish that the universe is headed toward a rip. Some recent combinations of data, including results from the dark energy spectroscopic instrument, have strengthened hints that dark energy may evolve. Hints are not a discovery. Different data sets and assumptions change the statistical significance, and the evidence has not reached the level required to replace the standard model. An evolving dark energy could move in many directions. It does not automatically imply a big rip. Another alternative is the Big Crunch. In the simplest early picture, enough matter and gravity could slow the expansion, stop it, and reverse it. Galaxies would approach instead of recede. The universe would become hotter and denser as space contracted. In a final collapse, conditions might move toward an extremely hot state, raising questions about whether a new expansion or bounce could follow. Current measurements do not favor this simple fate. The observed expansion is accelerating, not slowing toward reversal. A nearly flat universe with a cosmological constant does not recollapse merely because gravity exists. For a future crunch, the behavior of dark energy or the underlying laws would need to change in a way not demonstrated by present evidence. There are other speculative endings. A transition to a lower energy vacuum state could change the laws experienced by particles inside an expanding bubble. Such a vacuum decay, if physically possible, would not provide a warning signal traveling ahead of it. Cycles and bounces appear in some models of quantum cosmology. They are mathematically interesting, but no observation has shown that our universe will pass through one. The responsible answer is not to choose the most dramatic image. It is to assign each possibility the confidence supported by evidence. How can anyone study a future that has not happened? Cosmologists begin with observations of the past and present. The redshifts of galaxies reveal expansion. Type Ia supernovae trace how the expansion rate changed over recent cosmic history. The cosmic microwave background carries information from the early universe. The distribution of galaxies preserves a preferred scale called baryon acoustic oscillations. Gravitational lensing maps how matter bends light. The growth of cosmic structure tests how gravity and expansion compete. No single measurement is enough. Confidence comes from comparing independent methods whose errors and assumptions are different. The supernova measurements that revealed accelerated expansion were powerful because the explosions could be used as standardizable candles. Their apparent brightness and redshift together showed that the recent universe had not expanded as a simple matter-only model predicted. The cosmic microwave background offers a different kind of evidence. Its pattern of temperature variations constrains the geometry and contents of the early universe. Baryon acoustic oscillations provide a standard ruler. Pressure waves traveled through the hot young cosmos before atoms formed, leaving a preferred scale in the later distribution of galaxies. Projects such as decay map millions of galaxies and quasars across enormous volumes. By measuring that preferred scale at different redshifts, they reconstruct how expansion changed with time. Weak gravitational lensing supplies another test. The gravity of foreground matter subtly distorts the shapes of background galaxies, revealing how structure grew. If dark energy changes with time, its history must fit all of these observations at once. That is difficult, because every survey has calibration limits, selection effects, and statistical correlations. Combining them can strengthen a pattern, but it can also expose tension between assumptions. The standard model of cosmology, often called lambda CDM, uses a cosmological constant, represented by lambda, and cold dark matter, represented by CDM. It explains a remarkable range of observations with a small set of parameters. Its success is the reason that hints of evolving dark energy are treated cautiously, rather than announced as a new fate for the universe. A replacement must do more than improve one graph. It must preserve the successes of the existing model, while explaining the discrepancies, with fewer or better justified assumptions. Future surveys from ground and space will measure supernovae, galaxy clustering, and lensing with greater precision. Those measurements may return dark energy to a value fully consistent with a constant, or they may reveal a reproducible evolution that changes the distant future. Until then, the honest forecast includes both a leading path and uncertainty around it. The equations of general relativity then connect the contents of the universe with the evolution of its scale. Change the density of matter, radiation, spatial curvature, or dark energy, and the predicted future changes with them. Scientists are not watching the final night through a telescope. They are testing which model can explain the evidence we see now, then extending that model carefully. The farther the extension, the larger the uncertainty. Will there be one last second? In heat death? Probably not. Time continues, while meaningful events become rarer. There may be no final clock that reaches zero. There is only a growing interval between the things that can still happen. In a big rip or big crunch, a finite time boundary could exist in the model. Yet the physics near the final extreme may require theories beyond those we currently possess. The last night of the universe may therefore be a metaphor rather than a date. There is also no privileged center from which the ending can be watched. Expansion happens everywhere, and cosmic horizons divide the future into regions that cannot exchange information. Every observer carries a different horizon. No one receives a complete final report from the entire universe. And now we return to the present, when stars still shine, galaxies are still visible, and the ancient background light can still be measured. Our era is not important because it occupies the center of time. It is important because it contains evidence. We can observe a living universe and reconstruct much of its history. We can measure enough of its contents to ask what futures remain possible. The main picture supported today is an expanding cosmos, moving toward a colder, darker, more isolated state. Heat death is the leading destination, if dark energy is a cosmological constant, and known physics continues to apply. The Big Rip requires a more extreme form of dark energy that has not been established. The Big Crunch requires the expansion to reverse, which current evidence does not indicate. Every conclusion remains open to better measurements, especially measurements of dark energy and fundamental particles. Perhaps that is the quiet meaning of the universe's last night. The far future is not a prophecy delivered to us. It is a boundary drawn from what the cosmos has allowed us to learn so far. One day, the stars may vanish, black holes may evaporate, and usable energy may become almost impossible to find. But that day is separated from us by intervals so vast that the present universe is still extraordinarily young. Tonight, the sky is not empty. The sun still burns. The Milky Way still carries the light of hundreds of billions of stars. Distant galaxies still send us messages from ancient time. We live before the final darkness, while the universe can still look back at itself through conscious eyes. And for now, that is where the cosmic clock remains. Not at the end, but here, beneath a sky still full of light.